very long, very wide, so it can only fly at like a certain, like a limited speed. But if it's like a Air Force jet, it has like a short and very stiff wing. It can just fly like a very fast, like a 3 times sonic speed.
Right, so that's the problem with bigger modules. Effectively means that the wind load increases and you have to accommodate that in the design.
Yeah, exactly. So the stiffness of a solar tracker is, I didn't show that in this slide. I can probably just speak.
Yeah.
The stiffness of a solar tracker is actually based on the length between the fixed point, which is the motor in the middle, and the free end, which is like the both end of the solar tracker. Yeah, so let's call this one L. And with the new model, the new PV model, this L has become longer. Yeah.
Right.
Yeah.
So you mean between motor and the end of the torque tube?
Yes.
L is the length of the torque tube.
Yes.
Right, and it's become longer. How do you then, maintain all that stiffness by going longer?
Okay, we can probably maybe go further into this.
Yep,
so
sure.
Probably we can use some wind tunnel test to explain this this effect. So before that, I can probably maybe give some briefing of the wind tunnel test. So wind tunnel test is used to collect some design coefficients and to understand the tracker behaviors. I know many manufacturers or many tracker providers in the industry said, hey, we have our design tested with the wind tunnel, so we are like safe or bankable, but that's not really true. Wind tunnel test is to give you a very subjective understanding of your design, but you still need to be a very, very good design. And let's look at this chart. So these charts comes from the wind tunnel, multiple wind tunnel test. So you can see there are some dots above, and the bottom axis represent different angles, and the left hand side, like this y-axis represents the critical wind speed. I'll explain that one by one. So let's look at these triangle dots on the bottom right. So that means I stole my tracker at 44 degree. I think this is the a positive 44 degree. So it's like a how to say?
0 degree would be horizontal.
Yes, 0 degree will be horizontal. Minus will be like a nose down towards wing. So maybe we can call this like a nose up.
Nose up. Okay.
Yeah.
40 degrees nose up.
That's
gotcha.
correct. Yes, and then we increase the wind speed in the wind tunnel. Yeah, and once the wind speed reach like this point, the tracker get deflated like so heavily and can be damaged. Yeah, and the square like there's like a square dots below it represent another test, same angle, but the tracker get damaged at like a lower wind speed. So we just set the tracker actually to like a little model in different like angle and do like the test in like different times, multiple times, and then we have all these dots, and we can find that all these dots, they are actually above a certain line.
So the safety line is the black line. So below that is safe.
That's correct. Yes.
And above that, there are potential damage points for different test conditions.
That's correct. Yes. So we call this line the critical wind speed.
Ah.
So critical wind speed means for a certain design at a certain angle.
Yep.
Yeah. The tracker will start to get damage.
So I can see with this graph that at around about minus 15 degrees, it doesn't make a lot of difference. You've got the same critical wind speed.
Exactly. So the one thing I would like to point out is this curve has already been optimized. Yeah. If the tracker does not have a damper or spring to help to manage the deflation, this curve will be more like a V. So you will have a lower curve at like a shallower tilt angle here. Yeah. So this one has already been optimized. So you can maybe safely stow at like minus 20 or minus 30. That doesn't seem to have like a very big difference. But still, what I would like to point out is